if it's visible to you. Right now I'm sharing the solar constant slide. Is it visible?
Mm,
Yes, ma'am.
yes.
Okay, and straighten. Pratyusha, you need to mute yourself. I can hear Deepak. Great, thanks. Okay, so this is visible. How? What we have seen, sun is the ultimate source of energy for the surface of the earth, and sun is radiating outwards radially, and the outward flux will decrease in inverse proportion to r square. So the position of the planet will determine the amount of insolation we are going to receive. And it has been about 4 billion years since the formation of solar system, and earth has come to a radiative equilibrium with respect to its external environment. What do we mean by radiative equilibrium? That whatever it's absorbing, it's emitting accordingly. And we can apply some of the fundamental laws of radiation when things are in radiative equilibrium. And I'm going to share the whiteboard and you guys let me know if it's visible to you. Visible? Someone needs
Yes.
to reply. Oh, great. So, what is the black body radiation? A black body is something that absorbs EM waves of all the frequencies, of all the wavelengths. And once the black body is at equilibrium with, is at steady state with its environment, it starts emitting. Now the emission spectrum of that black body is going to have a characteristic frequency emission, and that's going to be determined by its temperature. So on the x-axis, we have wavelength, and on the y-axis, we have the intensity. And the emission spectrum looks something like this. And let's say I have another emission spectrum that that looks like something like this. Okay, and this is at T1 and this is at T2. T1 is, we will find out what's the relationship between T1 and T2. So first we will look at the general characteristic of this plot. Intensity of emitted radiation for every wavelength increases with temperature. So actually I've already told you increases with temperature. That means T1 is T2. So that's quite apparent, right? For at any given wavelength, the intensity is going to increase with temperature. So if a body is at, let's say, 300 Kelvin, let's say 3000 Kelvin, and the other one is at 300 Kelvin, they both are radiating, but their intensity is going to be different for one particular frequency or one particular wavelength that we are considering. Second is area under curve. So area under curve is going to give us the total radiation. So area under the curve for the body, which is at T1, is actually higher than the area under curve for T2. Henceforth, the total radiation given by T1 is going to be more. Third point, the peak shifts for every temperature. This is Wien's law. So for T1, the peak of its emission is actually at, let's say, lambda 1. And for T2, the peak of its emission is at lambda 2. Okay, so can anyone tell me what's the relationship between lambda 1 and lambda 2? Are they, which one is greater and which one is smaller? Uh, I will start asking question one by one. So Rashi, can we get started with you? Lambda 1, is lambda 1 greater or lambda 2 greater?
I think it'll be lambda 2 greater because of Wien's law.
Yeah, exactly. Lambda 2 greater than lambda 2. So the actual relationship because of the Wien's law is lambda max is equal to constant divided by the temperature. So it's an inverse relationship with temperature. So higher the temperature, shorter the wavelength. That means X-ray is going to have the shortest wavelength and the microwave is going to have the longest wavelength. First comes X-ray, then comes UV, then visible, then IR, and then microwave. Okay, and in the class, if you remember, okay, I'll share my text up again. Okay, so in the class, if you remember using the Earth's energy budget, using the Stephen Boltzmann law, we came up with the temperature of the Earth, which was minus 18 degree. But that's not exactly the temperature of the Earth. So where did we go wrong actually? This is a very huge offset, right? About 30 degrees Celsius of offset between what we have calculated and what we actually got. So we didn't take into account the atmosphere of the earth. The atmosphere has gases, so when the radiation is emitted from the earth's surface, atmosphere absorbs some of it and sends it back to the earth again. So earth is not able to radiate with its full black body potential because atmosphere is holding some of the heat, and that's apparent from this plot. If you look at the sun has a temperature of 6000 Kelvin, so its peak radiation would be at a much lower wavelength compared to the earth, because earth has, let's say, about 255 Kelvin. We can even consider it 300 Kelvin. It will be a minor shift in the wavelength. So coming back to the sun, this is the frequency spectrum of the sun at 600 Kelvin, and its peak wavelength is lies in the visible radiation spectrum. Okay, when we come to the Earth, at the temperature of the Earth, its peak radiation, uh, peak wavelength at which Earth is emitting lies in the IR range. Okay, so what's the problem if it lies in the IR range? The problem is lies in the gases in the atmosphere. If you look at this plot, the CO2 has the same absorption spectrum in the same range of IR radiation. Okay. Uh, do we know why CO2 is a global greenhouse gas? Okay, we will come back to that later. Okay, I'm going to repeat this point again. Earth has way lower temperature than sun, so Earth is going to emit at in the higher spectrum range. Now there are gases in the atmosphere. There is H2O, there is CO2, there's of course nitrogen and oxygen and argon. So what happens? CO2 absorbs some radiation. Every gas has some characteristic absorption spectrum, which is determined by its molecular structure. It so happens that CO2 absorbs in this range, around something like 1 to 10 micrometer of the range. CO2 absorbs energy and then it radiates back. So part of the radiated back energy comes back to the earth. Henceforth, earth is not able to radiate completely to its black body capacity. And we have other gases too. We have nitrogen, we have oxygen. So are those greenhouse gases? Uh, can anyone tell me? Are those greenhouse gases? Hello? Okay, Rohit. Rohit, it's your turn now.
Nitrogen and all are usually not greenhouse gases because their spectrum does not come in the higher range of the Earth's emission.
Exactly, perfectly. And the reason lies in their structure actually. So nitrogen is N-N bonding, so they share their charge equally. They don't have the dipole moment. When it comes to oxygen, again it shares charge equally. But when it's come to CO2 and H2O, they do have dipole moment. They're not sharing their charges equally. Hence, they have a lot of vibrational movement involved with their molecular structure. So we do understand till this part that CO2 is the greenhouse gas, and water is one of the greenhouse gas too, water vapor. But we cannot do anything with water vapor. But of course, CO2, the current concentration is because of anthropogenic activities. Moving on, distribution of insolation on Earth, is it uniform? Sagnic, distribution of solar insolation, the solar insolation that is reaching Earth, is it uniform with respect to latitude?
No.
Perfect. And what's kind of distribution we have?
Near the equator, the intensity should be more and it should be lesser towards the poles.
Yes, perfect. So that's the kind of distribution we have, and it's actually S naught cos phi by pi function it's following. So at the equator we have the maximum intensity, and at the poles we have the lowest intensity. Uh, Now I give you the plot. This is the emission plot of the Earth, and these values are coming from the instrumental measurements. So what do we observe? That these areas are heat deficit areas, energy deficit. I think I should do it in red. Red is the one that is coming from the sun, and the black is the one that we are emitting. So these are actually the can you see the screen? Okay. I hope it's visible. I was drawing the spectrum of the solar radiation. Okay. And this part is actually the energy surplus area. Overall, we have differential heating with respect to latitude. So excessive heat at the equator and heat deficit near the poles. So is it sustainable that one part of the planet is getting heated and heating and heated, and the other part is getting depleted and depleted and depleted? That's where the air and water circulation comes into the picture. So air and water circulation is going to move heat from hot to cold region, and they're trying to balance out the local heat budget. Because of this differential heating, we have very dynamic atmospheric condition. So we will go into that. First, we have the temperature difference. Why do we have the temperature difference? This is because of the because Earth is spherical, and each latitude doesn't get the same amount of insolation. So this temperature gives rise to the density difference of the air. How does temperature affect the density of the air? Sai, it's your turn, I think.
Hotter air is less dense as compared to the cold room.
Perfect. So hotter air is less dense too. So where are we going to find the hotter air? The area which is getting the maximum solar insolation, right? So this is going to give the density difference. And density difference is going to give rise to pressure difference. Is anyone going to volunteer how density difference is going to give rise to pressure difference?
Higher the density, higher the pressure.
Higher the density, more the pressure it's going to exert on a surface, right? Perfect. And pressure difference is going to give rise to the winds. So winds move from higher pressure area to lower pressure areas, right? And these are the wind which are going to which are going to elevate the temperature difference between two regions. Keeping this in mind, we can draw a atmospheric circulation model for the Earth. It's not a very circular Earth, but we will assume for the timing that this is Earth. So at the equator, what is happening at the equator? Tanish, your turn. Do we have hot air? Do we have cold air?
We should have hot air,
Yeah, right.
so that means there will be a low pressure there.
Exactly. So, right. We're going to have hot air at the equator, and hot air has low density, and it's going to be more buoyant than its its surrounding. So it's going to rise. As the hot air rises, this is going to create a low pressure zone at the equator. And at the poles, what is happening? It's exactly opposite. So poles are cold air region. So uh, everyone can see what I am drawing, right? It's a earth, and at equator it's a low pressure zone. And perhaps you can adjust your whiteboard just in case you're not able to see what I am drawing. Someone is writing something. Yes. Oh, perfect. Okay. So we'll write it as high pressure with red. Why do we have high pressure at poles? Because poles are cold. So as soon as air comes in contact with the ground, it's going to get colder. And cold air is very dense air, and dense air is going to give rise to high pressure. And air moves from high pressure to low pressure. So at the surface, what's going to happen? We are going to have movement of the air from pole to equator. Okay. And in up in the atmosphere, what's going to happen that the rising air, it cannot keep it will not keep on rising because there is a barrier that is tropopause. So this is troposphere, this is stratosphere, and in between there is a barrier tropopause. So troposphere and stratosphere have a huge temperature difference because stratosphere absorbs uh, which uh, which radiation stratosphere absorbs? Anyone? Tejas, any idea? Okay, stratosphere absorbs ozone. Sorry, stratosphere has ozone, so it absorbs UV radiation. So either way, the air won't keep on rising and it will deviate from its path and move towards the pole. And at the poles, it's going to sink. So that's how we get a closed loop that uh, here air gets hot at the equator, it rises up and then it moves towards pole. And at surface, what do we have from high pressure zone to low pressure zone? We have the surface air movements. Now what happens because of the big size of the earth and because earth is rotating, we don't get one single cell of the movement. We don't have one closed loop. We have three cells of the movement. So now we will go to the real picture of the earth.
Ma'am, I'm
Yes.
not able to follow like the way you're sharing, like drawing the diagrams. I don't know, like, can you like move the whiteboard when you're drawing?
Okay, okay. Rashi, I think try adjusting your screen whiteboard. Perhaps that might help.
No, I
Pen and
mean,
zoom. Hmm?
can you like draw something now so that I can like just see if I'm able to follow up?
Okay, sure, sure, sure. So I have drawn a, I'm right now drawing another earth. So can you see that?
No.
Okay, okay. So what can you see in your screen?
The UV radiation part.
The UV radiation part. So can you move right,
Oh yeah,
right on your whiteboard?
yeah,
So now you can see that.
yeah,
So there's one small circle and there's another one that's come a little
yeah,
bigger, but I'm going to raise it. Okay, it's visible,
yeah.
right?
Can you like
Okay.
just tell when you're like drawing a new figure because I think we're
Okay,
not
sure,
able to.
sure, 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 sure. I will keep that in mind. Right, right, right. Well, this is really hard drawing a sphere. Okay, this looks like asteroid, not Earth, but we will assume this is Earth.
ಜಾಸ್ತಿ ಅಂದ್ರೆ 10 ಜನ ಇದ್ದೀವಿ ಕೊರೋನಾ ಒಂದು ಹೊಸ ಸ್ಟ್ರೇನ್ ಬರ್ತಾ ಇದೆಯಾ
Again, the same thing at equator. The air is going to heat up, its density is going to decrease, and hence it's going to rise. And we are going to have a low pressure zone at the equator, and the air is going to rise. When the air rises, one uh, one thing happens that air is going to expand a little. So when that parcel of air expands, it does work on its environment by pressing out. So it decreases the amount of energy stored in that parcel because it has done work on the environment. So what's going to happen to that parcel of air as it rises? Its temperature is going to drop. So that is known as adiabatic expansion. So this parcel of air, everyone can see, like I'm drawing the air rising up in the atmosphere.
Yes.
Okay, great. So, what did we discuss? That as it rises up, it's going to adiabatically expand, and as it expands, it's going to lose its temperature. It's cooling down, and again, it there is a tropopause that's barrier, and it changes its direction. Now, because Earth is a very big planet, it doesn't have so much of the potential energy stored in it that it can go all the way to the pole. And there's one more very important factor that comes in, that if you consider the volume here at the equator and if you consider volume at the 30 degrees north, this volume is way, way less than the volume at the equator. It's not very apparent from this figure, but had it been completely spherical, then you would have, easily guessed that the volume here is comparatively less, way, way less than the volume at the equator. Hence, this parcel of air, which has started from the equator, and by the time it reaches 30-degree north, what happens? It's going to be compressed because the volume has decreased. So as it compresses, what happens to the temperature? As it was expanding, it was cooling down. As it's compressing, it's getting heated up. So this air is getting heated up, and finally what will happen? It will sink. It will sink back to the surface of the earth. And this sinking back of the air, this piling up of the air on the surface is going to create a high pressure zone. I hope every one of you understands why it air is being compressed, why air is sinking down. Air is sinking down because its density has increased. Its density has increased because it has undergone the compression. And as it sinks, this creates a high pressure zone. Do remember the order of the events. It's not a high pressure zone. The sinking of the air created this high pressure zone. And at the surface, so what happens at the surface? Wind moves from the high pressure zone to low pressure zone. Now we will look at the poles. At the poles, same story. Poles already know, we know that they are cold region, very cold region, coldest region in fact. So they are definitely going to have high pressure. The air is definitely going to sink here. So as the air sinks here, it creates high pressure. And whatever lies south to the pole is going to be low pressure because it's going to be at lower temperature. So the wind is going to move from high pressure to low pressure. I'm talking about the surface. And to complete this circular cell, air is going to rise here and then move towards the pole in the atmosphere. So these two cells, this is known as equatorial cell is known as Hadley cell, and the polar cell is known as polar front, I think. Polar cell. So these two are actually thermally driven cell. But the cell in between, so the air that is rising here, some of the air actually moves towards south. And this yes. The middle cell is more or less to complete the circulation pattern. It's not thermally driven at all. Thermally driven are only two cells, the Hadley cell and the polar cell. The cell in between is just completing the void that has been created by these two cells. I hope everyone is clear on that. Do we have doubts here?
No.
Okay, great. Now, this is Rashi, you,
You had mentioned that there's compression because there's a change in density, and again you mentioned that the change in density is compression.
No. Okay. There is compression that leads to density, that leads to compactness, right? That leads to increase in density. You are talking about this cell, right? Equatorial cell?
Yeah.
Right. So when the air is sinking back, so why is air sinking back? Because it started with way more volume, but by the time it reaches 30° north, the volume has decreased. The volume it was occupying at equator and the volume it's occupying at 30° north, it has increased. That leads to the compactness of the, now air is more compactly packed. So that leads to increase in the density of the air. And as the density increases, the air sink back to the surface. And that creates high pressure zone at 30° north. Okay, great. So this is an overall picture, but what is actually happening on the surface? Like these are the longitudes. So we assume that the air should be parallel to the like the surface air, which is coming from high pressure to low pressure. These should be parallel to the longitudes, but that's not we observe. That's not the real phenomena that's happening actually. They are being deflected. And I'm going to shift towards right and draw another Earth. So I've shifted towards right and drawn another Earth. I hope everyone of you can see that. So we will again start with the equator. So from equator, we are moving towards north. That's what the uh, this is just for the example. We will come back to the parcel of the air that was moving from 30° north to equator. But right now, what we are doing, there is a parcel of air that's moving, perhaps there is a cloud that's moving from, let's say, from equator to up north. And that's the trajectory that we assume. But what happens along with a vertical velocity component, along with a vertical force, there's going to be a horizontal force acting on it, and it's a pseudo force by the virtue of the rotation of the earth. So 24 hours earth completes one rotation. So in 24 hours, this point has traveled all the way. How much has it traveled in 24 hours? Rohit?
It's traveled across its circumference once, the Earth's circumference.
Yes, so that is 2 pi
2 pi r.
r. Okay. And let's say,
6,500-ish kilometers is what
yes,
I read.
exactly. Perfect, perfect. And let's say at 30° north, has it traveled the same distance? If there is a body at 30° north in 24 hours, has it traveled the same distance? No, right? Because the radius has decreased. So the body that has started, so what does it mean that the equator, we are moving at a faster rate. We are spinning at a faster rate as compared to 30° north. So what happens that the body that was leaving the equator and moving towards north is going to have a horizontal component to its a horizontal component to its force diagram. Yeah, we used to draw the force diagram. And by the time as it travels up, this horizontal force is going to deflect it from its trajectory. And that's the new trajectory. This is going to be the real trajectory of the body moving from equator to poles. Why is it so? Because by the virtue of the inertia, while it was at equator, it was traveling at much faster rate. But as it moves up, that faster rate is going to maintain, is going to maintain its force over the body. So overall, this was a we implanted to the body, and this was the force that has arisen because of the rotation of the earth. So overall, this is going to be the net force being applied to the body as it moves towards the pole. I hope we are clear on this, and this is known as Coriolis's effect. So whenever we are covering huge distances, kilometers, so Coriolis force comes into effect. Someone is writing something. Someone has written down the formula 2mv cross omega. Perfect. So m is the mass of the body that is moving, and v is the velocity of the body that is moving, and omega is the rotational speed of the earth. So the cross product of it. And how is it going to be dependent on the latitude? Whoever has written the formula. Is it Coriolis force? Is it dependent on the latitude? No. Actually, yes. When you how so, right? When you take omega, this component, this is going to vary with latitude. This is not fixed for for every latitude. So that's how. Velocity, that's what you have provided. Mass is fixed, but omega is constant. Omega magnitude is constant, but omega direction is not constant. Omega is constant for Earth, yes, it is, but its direction is not constant for every latitude. And that's why we write it in the term of vector and not just the magnitude. Otherwise, we would have just written the magnitude, right? Anyways, so there is going to be another Earth. So in northern hemisphere, any object that has a vertical velocity, Coriolis force is going to deflect it towards its right. And in the southern hemisphere, Coriolis force is going to reflect towards the left. And I'm shifting towards right. I hope everyone is keeping pace with me. And if an object is coming from, let's say, from pole to equator in northern hemisphere, Sai, could you please tell me where would it be reflected, like in the positive direction, or sorry, in negative?
Negative.
Yes, so it's deflected towards right. I have already drawn this diagram, but okay. And in the southern hemisphere, it would be deflected towards its left. So we will go back to our diagram. Can we draw it here? Okay, I'm going further right. No, we can just oh, screen share. So, I'm sharing the slides. This is the title is Planet Earth, and as you can see on the surface, the in the Hadley cell, the surface winds are being deflected, and they are coming from north to equator, so they are deflected towards right. So we don't have winds parallel to the longitude. Instead, we have winds that are about, we can't say 45 degree, but about 45 degree deflected. And in the assignments, has everyone, I hope everyone has gone through the assignments. In the assignment, there is a question about hurricane. So we will see how do we have this hurricanes. Okay, by the time. Okay, fine. Why do we have low pressure zone? Anyone? In the assignment, one of the necessary condition for formation of hurricane is low pressure, sorry, is high sea surface temperature, right? So high sea surface temperature is going to give rise to low pressure zone. So at the surface, what's going to happen? Because it's a low pressure zone.
Wind is
So
going to rush in.
yes, wind is going to rush in. Perfect. So wind is going to rush in, and that's how we expect that the winds will rush in. And do remember the scale uh, of the hurricane. We are talking about 100 kilometer squares of area. Okay, it's not a small area. Okay, so the wind is going to rush in, and that's going to rush in from high pressure zone. Now, as the wind rush in, what happens? This is a vertical motion of the wind. So Coriolis force is going to act on act on the wind that are rushing from high pressure zone to low pressure zone. Okay, so this is wind one, let's say parcel of air one. So where is it going to be deflected? Rashi, would you like to answer? Is it going to be deflected like this, or is it going to be deflected like this? This is northern hemisphere.
I can't see your diagram again.
Okay, you need to, I think, move towards right.
Okay.
Can you see it now?
Yeah, I can see it now. I think
So
we'll
you
be
can see the
going
low
towards
pressure
the
area.
red, right?
So it's going to
Go
be
towards
deflected.
the red one. I don't know if that's the thing that you were talking about, but I think it'll be going towards the red one left, right?
Okay, so once again, which hemisphere are we talking about? We are talking about northern hemisphere. And Coriolis force is just the deflecting force. And how does it deflect? It acts at the right angle to the moving object. So these are the winds coming from high pressure area towards the low pressure area. Can you see in the blue, right?
Yes, ma'am.
Right. So what will be the right side of the this blue arrow? The green one or the red one?
The green one.
Yeah. So it's going to be deflected like
Like to
this,
the green one, yeah.
right? And okay. Rashi will answer this one too. So what about this one? This is going to be deflected this way or the red way?
It'll be the same, right? Green.
Yes, so it's going to be deflected like this. And similarly, this one is going to be deflected like this. Okay, and overall, it's going to form a anti-clockwise swirl like this. Okay, this is the eye of the hurricane. That's a low pressure zone. And this wind is hurling in and creating a swirl. So, this circular pattern arises because of the Coriolis force. Okay, then who would answer what kind of pattern would we see in the southern hemisphere? This is anti-clockwise pattern. Would it be the
Will
same?
no, it will be
Huh?
the opposite.
It will be the
Clockwise.
opposite. Perfect. Okay, so do remember the Coriolis force is
One
the very.
second.
Uh-huh.
I had a small doubt. Like when you're saying it's going to be like anti-clockwise, it's because you're following the green arrow's direction all over, and then like just
Yeah, exactly. Huh, huh. Rashid, do you think there could be other direction possible?
No. I mean, I was confused because I was trying to figure out the winds are going to start from that particular equator point, right? So if I follow.
Listen. First of all, we are talking about surface. This is taking place on the surface, let's say in one region. The surface sea temperature rises. Okay. So the water is going to heat up, the air overlying the water is going to heat up, and it's going to rise and it's going to create a low pressure zone. So it's not necessary that in the entire on the entire earth we are going to find low pressure zone in only on the equator. At the equator there is the constant low pressure zone, but otherwise too we can have low pressure zone specific to some region. Okay, and this is a seasonal phenomenon. Why can we have, okay, I'm going to share my screen again. Mhm. Okay, I hope you can see my slides. This is seasonal insolation for different latitudes. So, okay, so 180 is something like June and July. So, if you can see equator, the temperature is equator is less, and temperature at Tropic of Cancer and Arctic Circle is way more than equator. But if we take the average, equator is not going much variation temperature wise, but other latitudes are going a huge variation. So overall equator, if we take the uh, average for a year, so the overall the equator is going to be heated up more. That's why it's kind of constant low pressure zone at the equator. But it does move, that is ITCZ, but we don't need to go into that. But as you can see, the tropic, let's say we are going to follow this line, the green, Tropic of Cancer. So the regions that lie in the Tropic of Cancer are going to be heated very much in the month of July, August, September, right? Rashi, am I
Yes, ma'am.
right? So do remember when I say low pressure, that doesn't necessarily mean that it's always at the equator. It's a seasonal phenomena and it's a regional phenomena. I hope. Okay. Perfect. Huh, so we were looking at the formation of the hurricanes. I can go through it again if you like. Rashi, Rohit, Sai,
I think it's
I
fine.
understood this, man.
It's clear.
you understand, right? It's clear. Perfect. So I think you can tackle this question in your assignment. What else do we have? Okay, so we have seen the surface winds. Now we will move to Ekman transport. So how does wind affect the circulation of the ocean? I'm going further right. I hope you guys follow up with me. Uh, okay. I'm drawing the winds in black arrows. So as the wind is blowing on the surface of the ocean, so what do you think? What will happen to the superficial layer of the ocean? The wind is going to push along the water with it. Agreed?
Yes, ma'am.
So this is in blue. Uh, okay. Fine. So this is in the blue. So as the wind starts and it starts pushing along the waters, the surface water. We're just talking about the surface water, not the entire depth of the ocean. It starts moving along, let's say perhaps a few meters, not even kilometer, 5 meters, 10 meters, something like that. Okay, it starts moving along. And what happens when any body move in vertical direction? What will come into the picture? We're talking about kilometers of area, region.
Coriolis?
Coriolis. So it's going to act, let's say it's northern hemisphere. What Coriolis is acts towards the right of the moving object. So this is our Coriolis force. Yeah, I can do that. Yes. So this is the wind action. And as the water starts moving along, Coriolis force takes over. And what's it going to do? It's going to deflect the water. So at the surface, what we will have? We will have wind, we will have water, something like this. Surface water, and this was wind. So this was something like for 10 meters, 10 meters of depth. This is just an assumption, okay? We need to do it, disintegrated in dx terms and then integrated. But for making it easy, we are just assuming that this is 10 meter. Now, if we go further down in the ocean and further down 10 meter, so what we are going to observe that the upper surface layer is going to drag the bottom surface layer along with it, right? So this 10-meter layer, I'm going to draw it in green, will try to move along with the upper surface layer. Okay, and as soon as it sets into the motion, what will happen? Again, the Coriolis force will come into the picture, which will be acting towards right. So what will be the effect? This is in green, we have the drag coming from the upper surface layer. And in red, we have the Coriolis force. So what will happen? Again, we will take the equivalent of these and it will be something like this. Now we will consider another layer, which is, so till now we have considered two layers. One is top surface, another one is just beneath the top surface, and another one that is beneath, 20 meter beneath these. So the top layer will try to take along this layer. So as soon as no, we'll take green. So sorry. This is going to be, this was the direction of the top layer. And as soon as it tries to move along, there would be centrifugal force acting on it, and the net will be something like this. So what do we observe? We observe a spiral-like configuration. I am moving towards right. I hope you guys are following. So let's say this was the wind direction. The top layer moved 45 degree. The another top layer, which is coming from here, moved something like this. The another top layer move like this. Another one would be something like this. Another one would be something like this. And what do we get? We get a spiral kind of configuration. And the net effect, like, and this spiral lasts for something like 120 to 150 meter of depth. So what do we observe? The net effect. I'm moving further right. Keep following me. So what do we observe? This is wind direction. This is Coriolis force. This is net Coriolis force acting on the parcel of water, which is about 120 to 150 meter deep. And this is the net movement of the parcel of water, which is about 150 meter deep. So are we clear on the effect of wind on the surface layer of the ocean? That's very intuitive that if the wind is blowing towards north, the water, the parcel of water, the mass of water should be moving along with the wind. But that's not the case because we have Coriolis force, which is actually a deflecting force. So that deflects the water, and hence what we observe is that the water mass is actually moving 90-degree perpendicular to the direction of the wind. And this is cumulative water mass. The surface actually moves about 45-degree. It's about 45-degree. It's not fixed. It's 30 to 45-degree. Mathematically, when we calculate, it comes out to be 45, but it's being observed that it's something like 30 to 45-degree. Are we clear on the Ekman transport? Tanik, Sai, Rashi, do you have any questions?
No, ma'am, it's clear.
It's clear?
Yes, ma'am.
Okay, so who's going to tell me how does Ekman transport lead to upwelling? And where does it lead to upwelling? Can it lead to upwelling everywhere? I'm moving further right. Let's say this is the continental boundary. Okay, this is a land. Oh, we have already crossed 3. Okay, I'm going to wind up soon, and this is sea. This is ocean. Okay, can anyone just tell me if the wind is blowing here? The water, where should the water be going, in which direction? Rashi,
45
Lohit,
degrees. 45 degrees to the arrow right side.
to the right side, right. This is the surface water and the net water will be moving 90 degrees to the wind. So what's happening? The surface water is moving away from the land. There cannot be a vacuum here, right? So what's going to happen? The water from deep is going to replace uh, that vacuum that should have been created here. Perfect. And that's why that is known as upwelling when the deep water is coming to the surface. So wind action causes upwelling. Do we have any questions from Sir's lecture? From assignment?
Presently,
Yeah,
no, ma'am.
Presently, no.
in the assignment, there was this S0 mentioned, right? So that
S
is,
not right.
yeah, so that was the intensity for which the sun, right?
Uh, S naught is actually the solar constant. Okay. That is what per meter square the insolation that is reaching the earth. Uh,
Okay.
okay, so what was the value of the, it was something like 1380 watt per
Yeah.
meter square?
Yeah.
Yeah, so that is the solar insolation reaching the earth. Okay. Uh, but
It's not the one emitted by the sun, right? I
uh,
mean, it's not the intensity emitted at the surface of the sun, right?
no, no, no. This is intensity reaching the earth, but do keep in mind this is watt per meter square. This is not the absolute value,
Yeah.
okay? And S naught is fixed for one astronomical unit, okay?
Yeah.
So if one astronomical unit changes, then S naught will change.
Yeah. Yeah. That's fine.
Okay, perfect. Anything else?
Yeah, in the precision formula,
Yeah.
the one which Sir had mentioned in the slides was something like E sine omega bar, right?
Okay, so in the precision formula, we are going to take it to be, yes, sinusoid. So if this time, uh, what was the time period of the precision? It was something like 23,000 year. We are going to assume it
Yeah.
20,000 year. Okay. And I hope every one of you understand what is precision, or you just want me to go through it once again.
I mean, if you can go through it in like few
Okay,
minutes.
okay. Yeah, in few minutes, perfect. I'm going to move towards further right in Blackboard. Please follow with me. This is Sun and this is our orbit. So right now, how the Earth is tilted, let's say this is the month of January. So what happens in Northern Hemisphere in the month of January? Quickly, quickly, guys. Rohit, what happens in the month of January in Northern Hemisphere? It's winters,
More,
right?
yeah,
So it's winter. So the tilt is like this, right? Southern
yes, ma'am.
hemisphere is more towards the sun and northern hemisphere is further away. And at the extreme opposite, what should be it? It should be month of June, July, right? I
Yes,
hope
ma'am.
you, so the tilt is something like this.
Towards the sun for the northern hemisphere.
Yeah, towards the sun for the northern hemisphere. This is, let's say, 2000 right now. Okay, this is present condition, and what's been asked, that 10,000 years from now. So 10,000 years from now, what happens? The tilt, the angle is going to remain same, because this has been asked that you assume everything else constant. So this is Earth, but the tilt will change. So the tilt will be something like this. Angle is same. Okay, the tilt angle is same. It's just that the direction has changed. This is sun.
So the time at which summer occurs will change by 6 months.
Exactly. For northern hemisphere and for southern hemisphere, the distance is not changing, the angle has not changed. It's just that the time, the I mean, the month we are getting summer will change. Okay, this is precision. So this is after 10,000 years. Let's say if I had asked you about 5,000 years, what will be the case in 5,000 years?
It will not be tilted.
Yes, at this direction it will be tilted, but in January and July it will appear like it appears in the month of March and September, right? The tilt doesn't have any effect in the month of March and September. That's why they are called, what are they called?
Solstice.
Yeah, exactly. So the solstice will be occurring in month of Jan and July. Okay. And what we will do for the next lecture, in the chat box, just write down the topics that you want me to go through once again. So instead of repeating the same lecture again, I will just go through those topics that you want me to repeat. Okay. And I think I have already stretched it too long, and we can wind up the class right now. Yeah?
Yes, ma'am.
Okay, perfect. So submit your assignment, and for the next lecture, please make sure to write down in the chat box what topics you want me to repeat. All right, then. See you next week. Bye bye.
Bye.